Welcome to AI Podcast. Today we're digging into a new AAAI paper on robot task planning that blends graph neural networks with transformers and a clever way to grow training data. Short version, it reads a map of your room, listens to your instruction, and plans the next step better than the usual suspects, without leaning on giant prompt engineering.
I'm curious already. What problem are they actually trying to solve?
Long horizon task planning from language. Think of telling a home robot, make tea or clean the kitchen. It sounds simple, but the robot has to ground that sentence in the real world, keep track of where things are, and choose a sequence of actions that won't get stuck. Large language models can reason a bit, but they're brittle when the room is cluttered and they're expensive to run for every step.
Right, so the classic problem is the robot knows the words, but not the room. What's the new idea?
The authors, led by Soojin Jeong with Yoonseon, propose a planner that merges two strengths. A graph neural network reads a scene graph, which is basically a structured map of objects and how they relate. On top of that, a transformer models the sequence of steps over time, so structure plus memory.
Scene graph sounds fancy. Can you say it in kitchen terms?
Picture a mind map of the room. Nodes are objects like mug, kettle, sink. Edges are relations like on, in, next to, or filled with. The graph neural network passes messages along those links, so it understands that the mug is on the counter and the kettle is near the stove, which matters for planning the next move.
Exactly. And the transformer part is like remembering the recipe steps?
That's it. The transformer sees the recent history, the instruction, and the graph features, and predicts the next high-level action, like pick up mug or turn on kettle. It's like having one model for spatial sense and another for temporal sense, working together.
All right, but models are hungry. Where do they get enough training data for this?
That's the second big contribution. They use semantic-driven data augmentation. Instead of hand-labeling everything, they generate new variations of tasks and scenes in simulation. They tweak object placements and relationships in meaningful ways, like moving the mug from the table to a shelf or changing whether a cabinet is open. Then they auto-verify whether the resulting plan still makes sense and is executable. They also draft natural language instructions to match those plans, so the dataset keeps growing.
So it's like a coach inventing practice drills. Move the furniture a bit, change the play, make sure it still works, and then keep the good ones.
Exactly. And that coach also runs a quick scrimmage to verify each play, throwing out anything that would obviously fail.
Give me a concrete example. Say I tell the robot, put the mug in the dishwasher. What might the augmentation do?
It could generate a version where the mug is in the living room instead of the kitchen, or the dishwasher is full, or the dishwasher door is closed. The planner then has to adapt steps, like first open the dishwasher or first carry the mug across rooms. The verification checks that those steps are valid in the simulator.
Nice. Where do they test all this?
Mostly in Virtual Home, a simulator for household tasks where goals are programs made of atomic actions. They test in scenes with lots of objects and clutter. And they also deploy the trained policy on a real mobile manipulator just to show it's not purely a simulation trick.
Do we know how it stacks up against other methods?
The headline is higher task success than baseline planners. The big picture is consistent gains when the scene gets busy, which is when you need relational understanding. They also note that this approach is smaller and more predictable at inference than prompting a giant general-purpose language model for every step.
So fewer fancy prompts, more grounded structure. Why do you think the combo helps?
Because it meets the problem where it lives. The GNN encodes who is where and what's related, which is the core of household reasoning. The transformer keeps track of what just happened and what should happen next, which is the core of procedures. When you only use one of those, you either ignore structure or you forget context. Together, you reduce those blind spots.
And the data augmentation probably teaches resilience, right? If the mug can be anywhere, the planner can't overfit to one layout.
Exactly. It's like practicing the same song in different rooms so you don't panic on stage. The variation builds robustness.
Any caveats we should flag for listeners?
A few. First, auto-generated data can import biases. If the simulator tends to place objects in certain patterns, the model might pick up habits that don't generalize. Second, the whole approach assumes you can build a decent scene graph from sensors in the real world. If perception misses a crucial relation, like whether a door is open, the plan can go sideways. Third, some public summaries of the work don't list every baseline or precise metric breakdown, so we'd still like to see full numbers, ablations, and open-source code for reproducibility.
Right, and generalization beyond one simulator matters. I'd love to see it run in other benchmarks like Alfred or AI2 Thor, where language and navigation mix in different ways.
Totally. And I'd add a few future directions. 1. Make the scene graph dynamic and selective so the model focuses only on relevant objects rather than the whole apartment. 2. Allow interactive corrections, like a human saying, "Nope, the mug is in the study," and the planner quickly replans. 3. Bring in stronger safety checks so plans respect constraints in the real world, not just in simulation.
Let me push on the real robot piece. If I bring this system home, can it actually help me, say, tidy up after breakfast?
Today, it's more of a research step than a product. But it's moving toward a middle ground where you don't rely on a giant language model for every micro decision, and you also don't hand script everything. For simple, repeatable tasks in semi-structured spaces, this kind of planner could be quite practical.
So in a workplace or a lab that looks the same every day, it could be a good fit sooner than later.
Exactly. And as perception improves, it gets more viable in messier homes, too.
Quick recap, then. The paper mixes a graph neural network to understand the room's relationships with a transformer to manage the timeline of actions. They grow training data by semantically remixing tasks and verifying that the plans still work, which gives the model a lot of varied practice. In tests, it's more reliable than baselines, especially when scenes are crowded, and it even runs on a real robot.
Nicely put. My takeaway is this. Structure beats vibes. If you give a planner a clear picture of who's where and let it reason over time, you can do more with less compute than pure prompting, and you get plans that actually execute.
And my takeaway is that data matters, but not just more data, better data. The semantic remixing plus verification is like quality control for learning.
If you want to look it up, the study is called GNN-Transformer Task Planning Enhanced with Semantic-Driven Data Augmentation from a team at Hanyang University, led by Soojin Jeong and advised by Yoonseon.
All right, that's a wrap. Thanks for listening to AI Podcast. If you enjoyed this kind of deep dive, share it with a friend who keeps promising to tidy their kitchen with robots.
We'll be back soon with more research over coffee. Until next time.